In topology, the deep interior of a mathematical space often acts as a mirror for the fine-gauge anomalies of its outer boundary. Consider the Poincaré homology sphere, denoted plus sigma, or S3 modulo 2i. This compact three-dimensional boundary encloses a highly symmetric four-dimensional interior, the canonical E8 plumbing, W. This boundary carries a specific quotient orientation, inherited as the link of the minimal resolution of the complex singularity C2 modulo 2i. Up to conjugation, it carries exactly two non-trivial irreducible flat SU2 connections. We call them the Galois pair, representations Q and Q'. These two flat connections are tightly linked. They are interchanged mathematically by the Galois automorphism of the quadratic field Q adjoint root 5. We measure their footprint using adjoint Atiyah-Patodi-Singer Rho invariants. For Q, it is -73/15. For Q', -97/15. Subtracting them yields exactly -8/5, revealing a strict quantifiable mathematical asymmetry on the boundary. Given this precise gauge asymmetry on the boundary, we have to determine which specific structures inside the highly symmetric E8 filling can actually detect it. The mathematical analysis yields a strict structural dichotomy. The raw topological skeleton is completely blind to the asymmetry, while its tautological decoration reads it perfectly. To understand this blindness, we first test the manifold skeleton, the raw homology of the E8 plumbing graph. Mod 2, the intersection form of W is alternating and non-degenerate. Because of this, it decomposes into exactly 4 hyperbolic planes. Since the intersection form is even, we apply a mod 4 quadratic refinement, denoted script P. Evaluating this yields exactly 120 distinct classes equaling 2. The Weyl group acts perfectly transitively on all 120 classes, mapping them flawlessly into one another. Consequently, no invariant of this pointed quadratic space can mathematically distinguish the distant 6 node of Q' from any other class evaluating to 2. We can also test the final structural slot, non-orientable characteristic surfaces evaluated via the restriction route. Any complex or real vector bundle on W restricts topologically trivially to these surfaces. Their degree 2 classes simply restrict to 0. Because this coefficient restriction reduces down to a basic rank multiplier, the entire Galois difference identically cancels out. The E8 homological skeleton and its characteristic surfaces possess too much uniform symmetry. They cannot see the boundary's -8/5 difference. They are blind to it. Since the raw skeleton is blind, we must examine the mathematical data sitting on top of it, the tautological bundles. Each non-trivial representation defines a tautological bundle, denoted R alpha, which physically anchors onto the exceptional curves, or Mackay nodes, of the minimal resolution. These bundles satisfy a strict dual basis property. Their first Chern classes are perfectly dual to the exceptional curves they decorate. Tracing these bundles to the boundary at infinity, their flat limits correspond precisely to the connections Q and Q'. We extract data from them by computing their fractional charge, K, defined by integrating their second Chern character over the manifold. This table compares the fractional charge against the Chern-Simons invariant across 4 primary sectors, Q, Q', and their adjoints. In all 4 sectors, the calculated charge evaluates to the exact Chern-Simons invariant modulo 1. When we compute the charge difference in the adjoint sectors, it perfectly captures a positive 2/5 delta. The homological skeleton failed to register the anomaly, but the tautological bundles physically realize the boundary asymmetry as an exact difference in interior fractional charge. By what exact mathematical mechanism do the boundary's odd signature defect sum and the interior's tautological charge communicate with each other? The connection is Theorem 1.1, the affine conversion identity. The left side represents the boundary currency, derived directly from the Atiyah-Patodi-Singer G-signature defect sum. The right side represents the interior currency, relying on the Kronheimer-Nakajima character sums, acting as Dirac-Eta invariants. Through defect sum orthogonality, the sequence evaluates perfectly to isolate the dimension terms. The strict translation between these two currencies is driven by a classical trigonometric kernel. By substituting the squared cotangent of the half-angle with a specific rational fraction of the character, the math generates a precise scaling multiplier of exactly 4. This identity is rigorously sharp. Any trivial constituent in the twist applies a predictable, exact additive offset to the equation. The boundary Rho asymmetry and interior charge asymmetry are tightly bound. Through this affine function, they are the exact same character sum read twice. Geometrically and algebraically, we have to ask where this -8/5 asymmetry actually lives within the binary icosahedral group. This is the complete total character table for the group, consisting of 9 distinct conjugacy classes and their defining angles. The Galois automorphism acts as a filter. It completely fixes any value that lies outside of the irrational classes, leaving them unchanged. This leaves only the bolden classes, the 4 specific conjugacy classes where the characters are irrational and actively moved by the automorphism. Consequently, every fractional contribution to the -8/5 difference rests exclusively on these 4 golden classes. With this data highly isolated, we refine the standard Chern-Simons congruence into a strict algebraic equality. This results in the exact echo equation. The charge difference matches the virtual character's augmentation divided by the group order, yielding exactly -3/5. The canonical filling perfectly detects its boundary's fine Galois anomaly, but it delegates this intelligence exclusively to the tautological decoration of its golden Mackay nodes, leaving the homological bedrock completely blind.